Hello, this lecture is about cellular automata. At first sight, that is not really decoding nature because there's nothing natural about cells, as we will see. It's a very mathematical and algorithmic way. However, the development of these cellular automata is deeply rooted in the development of physics and understanding of complex systems in the 20th century. It is a very interesting story along which you can really deep dive into the history of science and how science in the mid-20th century is connected to war, to the struggle of ideologies, and to interesting groups of men working in particular in Cambridge in England and in Princeton in New Jersey. So what we will look at is algorithms and Turing machines. Those are not strictly speaking cellular necessarily, but are very closely connected. You might have heard of Turing machines already in another context, but it's very interesting to see the common roots of both concepts. Then we will see the cellular automata as they are defined in one dimension, particularly with Stephen Wolfram's new kind of science, in two dimensions, which is the original way people had been looking at and building games and simulations, which we will particularly do in the next video, not in this one. So automata, as we has already mentioned in the Antikythera mechanism, have a long fascination for people, and these ideas that you have sprout wheels that interconnect and simulate natural processes goes back many thousand years. The rediscovery of that is in the time of the Enlightenment, particularly the French mathematician and philosopher Blaise Pascal with his Pascaline, a sprout wheel for doing arithmetics. It's the four species of arithmetics. That means adding, subtracting, multiplication, and integer division. This was broadened and generalized by Leibniz. So Leibniz is interesting in the development of mathematics in its own right, but also because he was this kind of adversary of Newton. I mean, involuntarily, I mean, they never met, they just stood in correspondence to one each other, and both thought the other would have stolen their idea of calculus. It is very clear that, that both had the idea of calculus, of infinitesimal mathematics, which became kind of the groundwork of post-Enlightenment physics, Newton's laws in particular, and the Leibniz idea of the derivative and the integral, which is the foundation of modern mathematics and then, in particular the analysis. So Leibniz is the first who understood that a calculating machine doesn't necessarily need to represent a fixed system of numbers. So he proposed a calculating machine that would be able to switch, for example, from the decimal system to a binary system. And probably he can be granted with coming up of the idea of a bit of the binary system as the basis for calculations, although he didn't go much deeper into that. In the 19th century, that was, of course, then much promoted. Calculating machines became very central to the financial system of the 19th century, doing accounting for insurances, for example. It became necessary to sum and make averages about huge tables like the birth and death of whole generations of citizens, namely in the furthest advanced European society, which was England at that time. Also, of course, for engineering, doing the calculations that would hold together systems like a bridge made of iron or a steam engine under great pressure. And one of the engineers who pushed that really the furthest is Charles Babbage. So Charles Babbage lived in London, and he was an interesting, very Victorian character with a lot of quirks. There's a lot of anecdotes about him in his fight against the street musicians using crank organs. I mean, he understood, of course, what a crank organ was. I mean, he was particularly fascinated by the Jacquard engine, the punch card operated weaver's loom, and he thought it was totally, I mean, horrible to use that to create music. However, Babbage's idea of an analytical engine was fully unfolded by his friend and for a time, co-worker Ada Byron. So Ada was the daughter of Lord Byron, the very famous romantic poet, and her mother was so afraid that her daughter would follow her father's footstep into the lunacy of becoming an artist. So she prevented Ada from doing any kind of art and forced her into a scientific career, which at that time, of course, in the mid-19th century was very unusual for a woman. But Ada was very privileged. I mean, came from the highest nobility and married very rich and became the Countess of Lovelace, under which name she is mainly found in encyclopedias these days. And so she could follow her interests, and seeing Babbage's ideas of an automaton, of a machine that would do calculations, she pushed it further and thought of making this programmable. And by that, she developed the first idea of a program language that means a mathematical formulation of algorithms that could be told to a machine. So I think this is a really remarkable turn in history, although unfortunately no one really at that time fully understood what Babbage and Byron would do here. And so their ideas were basically forgotten or not really thought viable. That changed then in the 1930s in a totally different school of thought driven by philosophy and the idea of axiomatic knowledge that was then formulated further by Alan Turing. We will go into that in a bit. There's a beautiful book about the whole history of mid-20th century philosophy and mathematics and all its struggles, written by the Greek comic creator and also mathematician Apostolos Doxiadis, whose grandfather was also quite a famous mathematician, who, I mean, according to Apostolos Doxiadis' small novel about his own history with his grandfather, became insane working on Goldbach's conjecture. So this book, Logic Comics, I think came out in 2006, tells the story of Bertrand Russell. So Bertrand Russell is a key figure in the 20th century philosophy of science. Russell studied in Cambridge philosophy and was deeply unsatisfied with the idealism of the, at that time, very fashionable Hegelianism in Cambridge. So that brought him to turn away from idealism, from the continental school of thought, and to thinking that it must be logic that is the foundation of science. Allegedly, although there is no real proof in Russell's biography, Bertrand Russell, sorry, went to Paris in 1903 to participate in the, so to say, in the centennial mathematical congress that took place there. And this is where many mathematicians of this time would lay the groundworks of 20th century mathematics. In particular, it was David Hilbert, one of the founders of modern logic, who gave a speech about that there will be no ignorabimus, there will be nothing that we will not know in science, because science is made, our perception is made in a way that we can detect the reality of the world. Hilbert here would follow the philosophy of Saint Augustine, one of the church fathers, who in late antiquity, in the 4th century of our time, looked at the world and would say that the world was made so that we could understand it, because we are part of the world, and our perception and thinking would only make sense if it would be adopted and adjusted by the world. This is actually what led then Charles Darwin also think of the idea of fitness, that, I mean, the world around us shapes our way of thinking, shapes our way of perception in a way that is suited to survive in the world. And Hilbert was very fond of that idea and says, why would there then be anything that could not be reasoned? And this paper that he wrote is very enthusiastic. So this is the his transcript, and it starts with, who of us would not want to lift the veil under which future is hidden? And so he really thought of this Newtonian idea that we will know and there will nothing be hidden. And Russell was deeply inspired by that and thought, we are far from that, but we should just start and write a principle of logic and mathematics like Newton had written a principle of physics. And Russell and his colleague Alfred North Whitehead would write that book, Principia Mathematica. And it is one of the least readable books that I had to touch in my own studies of mathematics. It is completely impossible, really, to follow the logicism that Russell lays out here. And Russell, while writing the book, became less and less confident that what he did would make sense. And so, in a way, he put that book out, and the book would find a lot of resonance outside England in particular. In Vienna at that time, a whole school of Viennese philosophers, they called the Vienna Circle of Analytic Philosophy, found that a major inspiration in their own striving to understand science in a philosophical way. The roots of modern statistics were laid at that time in Vienna also. So these philosophers would take Russell's book and find it very inspiring. In particular, a very young philosopher, Ludwig Wittgenstein. So Wittgenstein is kind of an odd figure in philosophy. He comes from a very rich family, one of the richest families in Europe at that time, so basically a billionaire son. But he didn't care about the money. He was interested in a lot of things. For example, together with his sisters, he would build a spectacularly modern house in Vienna, which is now the embassy of Bulgaria. You can visit the house. I mean, it's really modernity pushed to the edge. It was so cold and so hard that neither he or his sisters would actually want to live there, but it is a spectacle of modern aesthetics. And so Wittgenstein is a very extreme character. I mean, he went to First World War, and despite, I mean, his his social position that would have guaranteed him to just sit behind the desk. He would never be sent into the trenches because his family was so famous and influential. He volunteered and went to the front and always volunteered for the most dangerous and daring tasks to be assigned. But he never got enough of that. And in the trenches, he would lay out his ideas that becomes the Tractatus Logico-Philosophicus, the logical philosophical tractate that then became, in a way, the groundwork for a totally new school of thoughts in the 1920s after the war. In this Tractatus, Wittgenstein articulates a very thorough critique of Russell's system, which Russell didn't accept. However, already in the Tractatus, it becomes clear that just by laying a logical system of the world doesn't mean at all that we understand the world. It doesn't get us anywhere except reshuffling tautological formulations of the same things. So at that time, and Russell and Wittgenstein became friends, and Wittgenstein then moved to Cambridge also and started teaching there as a professor. After then, receiving the tenure and having a reasonable income, he just donated all his billions of fortune to his sisters and said, well, I would not become happy with them, but I know they are already unhappy. So let's just pile more unhappiness on them. You see all the privilege that speaks of that. The whole circle around Russell and Wittgenstein and all his friends was incredibly privileged. It's a center of British privilege, I would say, or European privilege at that time. All these men, they were so privileged that they could even be gay. They could even kind of lead the life of homosexuals in a time when it was strictly outlawed still. Another figure that entered that circle is called Gödel. So Gödel was probably the first person to actually fully work his way through Russell's Principia Mathematica. So page by page, he found many mistakes that Russell made and corrected them until he understood that the whole idea would only lead to contradictions. And he published his very famous theorem that no axiomatic system could be decidable. And this was a central breakthrough because it shows you that no logic system would be powerful enough to actually explain the world. And there will be infinite amounts of knowledge not accessible through whatever complex axiomatic system you set up. Well, during the 1930s, Russell became this total celebrity intellectual, particularly because of his, at the time, very unfavorable stand of pacifism. So he was thoroughly opposed against the British participation in World War I. He was even sent to prison for that. And so in the 1920s, when the European powers started rearming, Russell was in the center of the discussion about peace. And this is how he became, well, friends is probably too strong, but in a way, with the other most famous intellectual of the 1930s, which is Albert Einstein. So Russell and Einstein together had this debate about pacifism and became these icons of a peaceful humanity that is thriving. And so these most famous, so to say, faces of intellectualism in the 1930s are actually together in their publication, in their speeches, which they gave. So Russell and Einstein connect, and so do their circles. So here you see Einstein with Kurt Gödel in the 1950s. This is in the year, I think, when Einstein died in 1955, or maybe a year earlier in Princeton. So Gödel followed into exile because the Vienna School of Philosophy was strongly prosecuted by the Nazis. The Nazis were strictly against this idea of analytical philosophy and saw that as un-German. Gödel ended up in a way with Einstein, and they became very close friends. In fact, I mean, Einstein was Gödel's closest friend, and he became deeply depressive after Einstein died in 1955. And then fell into had these episodes of despair. So you see the connection of Einstein, the physicist, bringing together the minds here in Princeton. It's not Gödel whom we want to follow for the time being. It's another very famous mathematician who also came to Princeton and was a good friend with all of them, which is John von Neumann. So Johannes Neumann, John von Neumann, is an Austrian-Hungarian mathematician. You see him here hiding or kind of being half hidden in the doorway. Einstein goes in the center. He is the most well known. So John von Neumann had a lot of very original ideas. So first is game theory. So in the 1930s, he started thinking of a mathematical expression of any kind of games that have elements of probability into it, like board games where you throw the dice, or that are purely logical, like chess. And from that, he developed a system of rules, algorithmic ways of deciding games. This, of course, in the 1940s, made him incredibly valuable for the war efforts of the United States. So there's many game theoretical considerations in the war strategy that the United States pursued. Many decisions where to send ships, for example, if you have limited resources, and also the ideas that there are games that have only losers, there is no winners, like the idea of the prisoner's dilemma. So, and to how to avoid these games became very, very important to define after the war the strategy of the Cold War, of mutual annihilation, for example, of the flexible response, and other game theoretic answers to the nuclear armament, which is another contribution of von Neumann. So John von Neumann is also one of the major fathers of the mathematics of quantum physics. And both together, the idea of game theory with the quantum physics connects him to one of the most dramatic physical developments of the 1930s, which is nuclear fission. So in 1936, the Hungarian physicist Leo Szilard first attempted to try a nuclear chain reaction. He didn't succeed with that because he didn't have the theoretical background, I guess, and also not the means of it. However, a year later, the German physicists Otto Hahn and Fritz Strassmann succeeded by using enriched uranium, just like we would do today. The mechanisms were not understood by Hahn and Strassmann. However, by Lise Meitner, who used to be Hahn's co-worker at that time, she was already in exile because she was Jewish. She had to leave Germany. So Lise Meitner and her nephew Otto Fritsch issued the first real explanation what happens during nuclear fission. And although, I mean, probably their contribution to the discovery of nuclear fission is actually much more important than that of Otto Hahn. It was Hahn who was granted the Nobel Prize, and Lise Meitner wasn't, because she was a woman, as things at that time still were. In a way, the race to get further into nuclear fission immediately started. Within very few weeks, the French couple Curie-Guyot, so the daughter of Marie Curie, who discovered radiation, together with her husband, would work out the first, I would say, scalable advances in nuclear fission. And at the same time, in New York, the Italo-American physicist Enrico Fermi came to the same conclusions. And in 1942, it was Fermi with his team at the University of Chicago who would build the first reactor working with a chain reaction. So what is the chain reaction? Why do we say the chain reaction? And so what happens in the chain reaction is we have uranium-235, which is very rare, it's less than 1%, because it is quite radioactive. So over time, the deposits of uranium-235 decayed. So the much more stable uranium-238, which is barely radioactive at all, although it is highly poisonous, is like more than 99% of all uranium deposits on Earth. However, there is a small amount of, so less than 1% of uranium-235, and that can be enriched, which is a very costly and difficult process. It's an incredible investment that you need to do. Only the largest and richest economies in the world are able actually to produce significant amounts of fissionable uranium-235. Yeah, the uranium-235 is unstable. The core is unstable. And so it spontaneously breaks apart. So the core breaks into two halves, and the two halves are smaller than 50% of the original, because 4 of the neutrons fly apart with high speed, incredibly high speed. So usually nothing happens. They just radiate away and then decay somewhere, so that nothing really happens. But if you are able to slow down these flying away neutrons by adding a so-called moderator, which is usually graphite, that is put between the lumps or the rods of uranium, the speed of the neutrons is significantly slowed down, and by that the probability of the neutrons of hitting other cores of uranium is dramatically increased. So these neutrons fly and accidentally hit other cores of uranium, and by that make these cores more heavy, and then these cores break apart as well, and more neutrons fly around. And this is why it's called chain reaction. You start with one atom and then it flies around. This idea of understanding how the chain reaction has to be moderated is one of the inspirations that John von Neumann took in understanding automata. So what he would start in 1942 to work on the Manhattan, or 1943 to work on the Manhattan Project, which was initiated by Einstein's letter to the American President Roosevelt, warning Roosevelt that Germany would be way ahead in nuclear physics at that time, and would probably within a very short time be able to create nuclear fission as a weapon, as a nuclear weapon. And he says America has to be prepared and be able to retaliate if that happens. Otherwise, that would lead to German superiority in the Second World War. And he was his plea was heard, and so the government initiated a very secretive research initiative led by the research director Vannevar Bush, who's also one of the interesting figures in promoting computer science and then developing hypertext. So he can be granted the fame of being the original inventor of the idea of hypertext and the link. So, Vannevar Bush would then bring together the brightest minds in physics in a totally remote location in the Rocky Mountains in Los Alamos, in the deepest depth of New Mexico. I mean, even to this day, it is really very, very remote, this lab. And there they would come together. It was, I think, like 10,000 scientists and engineers also working on that project at its peak. John von Neumann was one of the leading scientists and mathematicians and tried to figure out many aspects of what had to be resolved before coming up with the theory that would actually work for the atomic bomb. And one is this idea of self-reproducing automata, as he calls this. So he would think of the idea of a chain reaction much more general than just as these atomic nuclei breaking apart. Von Neumann would think of robots that would take parts like raw material or so in the world and would self-assemble these parts to become more robots. Like we would see today, actually, the idea of self-replicating AI-driven artificial life. And so he would start thinking, how would that be possible? And his colleague Ulam, he would push him towards understanding these automata in a very discrete mathematical way, using only digits to represent them. So let's have a look at these automata. If you think of a chain reaction, you could think of let's simplify that here in our spreadsheet. That you have like you have the original states that would be atoms that are not going to fission, and then we represent an atomic core that breaks apart by 1. So it changes from 0 to 1, and we could think of this 1 sending out the neutrons to the neighboring atomic cores. So this is the first generation, 0, and then comes the next generation, 1 and 2 and 3 and 4 and so on. So you could think of that as time passing in discrete steps. And if we want to understand how likely it is for example, this cell H to break apart in the next step, this cell gets a function that is depending on its neighbors. So let's say, for example, if the sum of the neighboring cells, like let's take 2 of the neighboring cells into that account, and the cell itself, of course, also, is bigger than 1, this cell will also divide and break apart, and otherwise it will stay the same. So what we do here is we create a neighborhood. The neighborhood we create here is called the von Neumann neighborhood in one dimension. Of course, von Neumann didn't think of that one-dimensional. I mean, he thought of that as three-dimensional and then reduce it to two-dimension to a grid. But for now, for the sake of simplicity, we just take one dimension. So as if the atom cores would be just be like pearls on a thread. So when you see this, this cell is of course also zero, and then we just copy the formula. So of course this is wrong here at the edge. We should not take into account the things that are outside our edge here. So we start here like that. And now we can copy and paste that down. And now experiment what happens if, for example, this cell H breaks apart. Nothing happens because our rule was that we need at least two. Let's see, the neighbor breaks apart as well. And now you see the chain reaction happens. In the first step, it's 4, then it's 6, and so on. So very quickly, all the uranium gets into fission and breaks. Could also think of that it is only the cell in G and the cell in I, and again, that also breaks apart cell H. So, and you can of course, could of course then paint the grid that it changes color and so on. And what I demonstrate to you is the first example of a one-dimensional cellular automaton. It's a very simple rule that we defined that tells each cell how to behave in respect to its neighbors. And we think of time passing in discrete steps. Yeah, Stephen Wolfram's book, A New Kind of Science, when it came out, it received all kinds of enthusiastic criticism and a lot of, I would say, very negative press as well. So Stephen Wolfram, of course, is very famous as one of the people who made mathematics into a computable science. I'm totally following the idea of Russell and his time that only computable mathematics make sense in the end. And Wolfram created Mathematica as the software package for that. And in working with Mathematica and on his problems, started in the mid-90s to discover that there is some fundamental properties in many aspects of mathematics, but also in natural sciences and sociology and so on, that he boiled down to cellular automata. And although that's a bit, I would say that's a big leap. And as with the fascinating ideas about a new concept of quantum physics, as we started this lecture series early on, you remember this nice, very sympathetic piece by Rudy Rocker about Wolfram's new ideas on physics. I think there's a lot to be learned of and a lot to be very skeptical of. I mean, nevertheless, what Wolfram does is he reduces complexity in thinking about dynamic processes and the creation of complexity a lot. I mean, as with the fractals, creating complexity with feedback processes and recursion, cellular automata offer a way of describing very complex systems incredibly simple and computationally very, very favorable. And so it makes sense to follow Wolfram's book. I mean, it is completely available for free online. If you see it in print, it is beautifully made. It weighs a ton. It's 1,000 pages, big, very glossy paper, nicely layouted. So it's really a beautiful book. Reading it at the first time, however, I found it very disappointing how little I actually took away of it. I didn't know at that time, 20 years ago, that I would have to teach it at one point. Otherwise, I would have paid more attention, I guess. Well, so it starts in the second chapter with what Wolfram calls the crucial experiment. And the crucial experiment goes as follows. You have one cell, just as we saw in the von Neumann simulation of nuclear fission, of the chain reaction. You have one cell and the cell's neighbors, which define how the cell after that will look like. So for each cell in our line, for each point on that line, we define how that point will look like in the future by how the point itself and its direct neighbors look. And this is the notation that Wolfram develops. It's a very useful notation. So you see basically here, you see the cells. The cell in the middle is the cell we are interested in, and the example that was given above is translated here. So if all cells are empty, the following cell will also be empty. But if one of the neighbors or the cell itself will not be empty, then the cell will not be empty. And of course, we can just easily, instead of empty and not empty, write ones and zeros in the tradition of digital notations. So you see that we can represent, for example, all cells are empty with 3 zeros, and then like the right-hand neighbor of our cell is black, then that means 1, and the right-hand and the left-hand are black, that would be 0 in the middle, and 1 on either side, and so on. So you see, these are the configurations, and that is all the configurations that we can think of with 3 cells that have 2 states. So it's very simple, simple to just count them, and it is as simple, of course, then to use logical operations to describe what we are seeing here. So if you have the left, the middle, and the right cell, we just write it as the states. The middle cell 1 is calculated from the states of the left, the right, and the middle cell. Or I see I have the typo here. Let me just correct that briefly. Again, so as the left or the middle or the right. So that's the logical operations. And that leads to our desired result that in any case it will be 1, just if all 3 cells are empty, then it will be 0. And Wolfram says, well, since 2 of these rules have the same outcome, they are the same, we just need to enumerate these states of these outcomes, of these 8 different outcomes. I mean, 2 to the 3 is 8, easily to calculate that. And so we have, in this case, the decimal representation would be 254. So the binary number 1111110 is 254 in decimal. And that's the second highest that we can get with 3 bits. Yeah, and now we go into our canvas, into our editor here, and try to translate what we've seen in theory into the JavaScript code. So we don't have a function draw here. We call the function rule set f. This is how I called it. And what this function should do is we give an input, for example, 254, as in the example that we've just given. Any integer n should do. And the output of this should be the rule that is applied. I mean, like, for example, as in our example that we have been looking, the OR, that one of the three cells is 1, and then the next one is the OR. So this will be the function. So we will have an array R that is our result rule that will be an empty array. I mean, in other programming languages, we would have to specify that we mean an array of the length of 8. However, since our language here is JavaScript, that doesn't require it, we don't specify it. But that we keep in mind, our R should be an array of the length of 8. So we take in the integer representation in decimals and want to transform that into the binary transformation, in a binary representation. So that is, of course, done like this. N is translated to a string on the basis of 2. We get a string variable b that is the decimal representation of our input n. However, we need it to be exactly of the length 8, otherwise we would have a number that might be shorter than our 8 digits that we want to look at. So while our b is smaller than 8, we need also smaller than 2. We concatenate zeros as strings in front of our b. So that basically just fills our b until it has the length 8. So this is done. And now we have a loop that starts at 0 and goes through all the digits until 8, and of course gets incremented. And the rule is applied very simple. So if our position in our string b is equal to 1, we say that our R at that position will be 1. And else R at this position will be 0. And that's it, basically. I mean, we just fill our rule with zeros and ones according to our input. It's a very simple, I mean, kind of a way of basically transforming our input, which will be decimal, like 254, into first a string of zeros and ones of exactly the length 8 in binary representation, and then use that to return an array with 8 positions that are either 0 and 1. So this is what we have done here. We return the R. This is our function of rule set. And now let's move it up a bit. We have a second function we call the Cellular Automaton that will take rule into as input, and then we have to draw that in a way, to calculate that. So let's start defining a few constants here. So the automaton has width, so to say, which is the size of our canvas divided by another variable that we have to define. Let's call that width and take it in. It's basically the size of our cell. So if we, otherwise it would be 1 pixel cells, and we might want to draw the thing in a bigger scale. So this is all it does. It just scales the size of the canvas. And the cells is just an array. We know that this array would be the whole line, so that would be the length. There's actually the variable L here, but we don't need that as discussed. So, and then we initialize the first line with any random value. Let's just start with let's say that's again I is 0 to I is less than the length, which is this L, because we increment. And here we just fill the cells with zeros, except for the one in the middle. Let's just say if I is in the middle, but we can't know if that, I mean, if we have an odd number, that might be not very favorable, so we need to have the floor again of that. Then we have a 1. So that means that one cell, I mean, we just chose the middle cell, it can be any, of course, is set to 1. This is all this loop does. So, and we define another constant now, we call the generation. And we start with generation 0. That's basically our line with just one cell in the middle being 1. And the rule set, which is, we call the function now with our input R. So we have now an array in this variable rule set, which is what our function rule set returns. And we define a function that is called generate, and will be the function that creates the next generation from the current generation by calling the root and then manipulating the cells accordingly. So that's a function that has no inputs and calculating as follows. So we have next gen, which will be what we take in zeros and ones for the next generation, and we have a loop for always let E 0, so E is less than L and gets incremented. So we go through one cell after the other. We start with everything is by default 0. And now we have to look at the previous generation. So how is in the previous generation the neighboring cells? So basically we define variables left, the cell itself, me, and right, and look at the current values of the cells. The left cell is to the left. The cell itself, I mean, of course, is cell itself as it is the position I, and the right is the cell one up. And now we see also how we have to loop here, that we don't overshoot. We have to now start at 1 and stop at 1 earlier, so that we have the left and the right cells, and then go through and here. So we have these now defined, and then we say the next generation at the cell's position will be a new function that we will define in a second, that we call rules left, me, and right. So, typo. So, and then once we have called this function that we will define now, we just swap the generations. So we say now this cells will be the next generation, and we increase our generation count by 1. So now we only need the function rules as we have defined it here. So and we define that as this rules is a new function that takes 3 inputs, left, middle, and right. And the only thing that this function rules does, it calculates the binary representation for the left, middle, and right, like if that would be bits. I mean, it can be any number between 0 and 7, so 2 to the 3, as you understand. So the left cell is 0 and 1, so 0 and 1. Then the middle cell is can be 0 and 1, so that means 2 and 3. And the third And then, of course, the first bit can still alternate as the least significant bit. So all in all, we get the numbers between 0 and 7, and just have to translate the value 0 and 1 of our three inputs, left, middle, and right, into what number that is. So that is very easily done by just calculating our R as 7 minus 4 times A, that's the highest significant, plus 2 times B, plus C. So you can easily calculate that does the trick. Why do we need to have 7 minus that? I mean, that is the problem with normally writing numbers from left to right, but actually the values go from right to left. The least significant is the furthest to the right. And so we have to kind of reverse that. This is all why we have to take 7 minus this number. So, and that we return what is in our rule set. Yeah, and that's it basically. So in theory, our automaton is now ready. The only thing that we are still missing is, yeah, I think I have to place that up one hierarchy. Yeah, much better. Doesn't get yellow. So the only thing that is now still missing is a function by which we can display our automaton so that it gets a nice graphical representation. This is not necessary. I mean, everything is calculated here. So if you would just do math on it, that would be also absolutely fine. So, and this is, you know, again, very simple display function. So we have again loop through all the i's from 0 to the length of our array and increment. That's of course a mistake. So, and if the value of our cell is equal to 1, then we have a black cell. It's just how we draw it, and else a white cell. And now we just need to draw it. We just make a rectangle that has the side length. Let's look that up, how we called it. Sorry. Width. Call it width. And then the downward, the y-axis is the number of the generations, and that goes also with the width. And then the sides are just the width. So, and now I hope we haven't forgotten anything. I mean, let us just try it out. What comes? We create a new automaton. Let's say we have 10 pixels width and take our rule 254 and then we need our function draw to draw it. Maybe our canvas a bit bigger. And our function draw, we just call the display function and then just limit and this is our width here. Let's make it a variable. If we don't overshoot, and as long as that goes, we calculate our cellular automaton. And of course, it doesn't work because there's quite some typos in it. So here's one, of course, it's not cell 1, it's cell I is 1. This is weird sign. And then I messed up all the brackets. So first of all, we take the rule function here and the display function. Yes. And copy that down here. And still the same we do with the generate function. And let's hope that that works now. Still not. Let's look further into it. Yeah, it's very simple. We have this loop here that doesn't go down here. So, and now it works. You see, the rule is properly implemented, and we can now basically tell the machine no matter what rule we want to use. For example, let's say, for example, rule 8, it's a totally white rule, rule 9. And you get the point. There is a lot of beauty in this automata, creating all kinds of complex pattern. To save time, I've created a template that I'll show you that is, of course, linked in the syllabus documents, and you can try out all kinds of automata here the same way. And what I will show you here is that I put into a visualization of the rule according to Stephen Wolfram. So why don't you just have a look at that? This is it for today. In the next lecture, we will look a bit more in depth into certain examples of these cellular automata that have really surprising properties in terms of chaos and creating structure. And then we will expand that further into the two-dimensional or more dimensional cellular automata.